Hello, I'm back again with another project here. Today I'm going to present my course project for Introduction to CMOS VLSI Design EE414 at Bilkent University. The aim of the project is to design this block, which is a 64-bit programmable serial correlator, in hardware, in Cadence. So throughout this project, I've worked on four main things. The first one was the behavior design, which was made in VHDL. Then I moved on to the synthesis of the gate level design. Further, we've come up with the layout design and conducted some analysis. And finally, we've extended the design to incorporate the scan technique DFT into our design. Bearing in mind the potential use in telecommunications, we have many requirements. The first was that the data was to be fed serially. The design had to compare with two patterns. It had to detect and raise a flag, and it should have also detected the polarity. It was supposed to be programmable, and the program is also fed serially. And finally, it should have been able to operate during programming as well. So the way I've implemented this was to write a VHDL code and a test bench and run some simulations in Cadence Insys. Here you can see that we're feeding a parallel data in, and then the sync flag is raised at the pointed out point. This happened because a pattern is detected giving zero sum, and you can also see that the device is actually being programmed as well. After the behavioral design, I've synthesized the gate level circuit in Cadence Genus that you can see in the image. Once again using Genus, I've made multiple timing and power experiments, and I've chosen the best case scenario with the lowest energy delay product, which happened to be the 2.2 volt case operating in a 40 nanosecond clock period. Having decided on the parameters, I've moved on to layout design in Cadence Innovus. Here you can see the initial output of the auto-routing. The clock line, of course, required some optimization. To achieve better slack times, I've optimized the clock line. Then, I've added the power ring and checked the connections. So this way, the layout design was almost finalized as on the left. Then I've extracted the GDS file and opened the design in Virtuoso, which you can see with the pads. Here you can get a closer look from the transistor level with all the collections. The last step was to make the design testable. The idea behind the scan technique that I've used is to add an extra shift register line that connects all sequential elements in the circuit. This way, any desired pattern can be loaded into the circuit, and after running usual operation for some clock cycles, the results can be scanned back out, and they can be compared with the expected results. With this methodology, I've followed the same process of doing the gate level synthesis in Genus, and then I've also generated test patterns using Modus. Here you can see some timing analysis for the setup and hold times for both testable and non-testable cases. You can also observe the power analysis that I've conducted for these versions. Finally, the occupied area can be seen here. As expected, the testable core occupies 25% more area, but when we also consider the pads, it's not very important. So this marks the end of my presentation of the course project. Thanks for holding up until this point, and I'd like to thank you once again for your interest. And many thanks to Professor Atalar for his magnificent teaching efforts. Have a good day.